y'all? Got really Beverly Jr. here, back for some more physics. We'll go ahead and do some simple harmonic oscillation. And our main source will be the old textbook I had from undergraduate, Classical Dynamics, which is the textbook I like. I think is written pretty well. I'll do this show, then I'll come back an hour later and we'll do some special relativity. We'll do some simple harmonic motion first. I'll do frictionless, damped, and uh, with a driver. And then we'll do special relativity utilizing the example of a muon, made from cosmic rays, and its effect towards the Earth, and whether it makes it to the Earth or not. So stay tuned after this show. Or you can click in a moment those who come later. So we'll start with the 1D one. And I just remembered there's one thing I forgot to pull up. I'll load that. Here's my note. So I'll go through this pretty carefully. Hope I don't have any false starts. So we'll start with uh, a simple harmonic oscillator. Um, so we'll start with we're looking at the textbook with the regular equation. So basically we have our F equals MA. In this case, we're using a force, taking the Taylor expansion, the Taylor series expansion, um, expanding this out, taking the first order linear. Um, I'm unsure why they do it this way and not going straight to equals limit, but I guess we do that later. We do the second derivative thing, we'll see. So suffice it to say, if you have a simple harmonic oscillator, oscillator in one dimension, the force exerted by the spring is going to be a restoring force opposite the extension. So we have a spring in two dimensions like so, this in one dimension. This is our mass, and the spring is connected to a wall. The spring will have a K constant K, and if this is the equilibrium point where it's at, then X will be the amplitude about which it moves, and reach the maximum X. So, and we can see that if X is positive, the negative in the front stays negative, and thus the force is pulling back in this direction. So this direction that the arrow is going is the direction of X plus X. So as we go to the right on the number line, the numbers get bigger, more positive. So we push the mass to the right, the force will move it back to the left. And if we push the mass to the left, that's a negative X, the negative and then the negative cancel. If we push farther to the right. So we have that. So, okay, so here's the image thing that comes up. So we always get this. So if we can get well, I'm gonna go and say too much of the foundational principles there. But I guess it's because it just says the restoring force uh, we're only considering a function of fx. Mm. But the origin is 0 because if it's throwing force that it, or otherwise that it puts out, and it's just that the higher terms are smaller. So interestingly enough, we just have a force. We expand the term in the Taylor series, and instead of restoring force, the center point at the center point F is 0. Obviously, wouldn't be able to stay in equilibrium, and the higher terms cancel out, so it ends up being linear. So what we do now is we equate this to Newton's second law, which is what we get to on the next page here. And we can go ahead and get the uh, angular frequency. So what we can say is that x double dot equals negative k over m at, and we can define w naught squared as k over m. So this means that x double dot equals negative omega naught squared x. And so what we need to make this work, we need a solution because now we have a second order differential equation. We also write it another way. We have d squared x over dx squared equals negative omega naught squared. And is that bold enough? Let me make my text still a little bit bolder. Oh, I forgot. Mm, right. I'll go back to the previous one. Okay, was that right? Right. So now we have a second order differential equation. Another way to write this is like this. Oh, T. Mess up my notation. Okay, there we go. So either way it goes is fine. So there's no way to write it, other way to write it. When I saw the X out of habit, I was going to do the slash. So basically a dot means that you have a derivative with respect to time, and a prime means a derivative with respect to position. That's like the normal convention that's utilized a lot. So now we have a second order differential equation that we can solve to find out what form this motion takes. And two things work. So basically what we have is something that when you take the second derivative of it, it gives the negative of the original thing you had with a factor of something squared. So there's two things you can do. You can do the exponential e, and you could also do, which is the common thing to do, to trig stuff. So basically what we have is x of c equals a, and I'll go sine, but I'll go cosine. See which one the book does. It says it could be expressed in either of these forms. Um, we shall go the sine wave. X equals, well, we have sine omega naught t plus some phase. So that means x derivative with respect to time t equals. So we're going to have a cosine of omega naught t plus this. And using the chain rule, we have to take the derivative of what's in the inside with respect to t. Which means we have a omega naught that comes on the outside. And then we can take the second derivative of t, which is going to be negative a sine omega naught t plus, and actually, let's do minus on that, like in my example. And then we're going to have to take another derivative of the inside, which is square this, does not because there was already one there. And we can see how this does satisfy that we have negative omega naught squared, and a sine is our x of t. So we can put x of t back, and we can see that it does match. So that means that we use the book and recreate the Taylor expansion, but the book used the Taylor expansion to find is the force, where the force at the origin is 0. So we could ignore that. The larger terms will be very small because we're talking about a very small. So simple harmonic oscillation or small oscillations. So as long as you have a small oscillation, if you take the square of that very small thing, it'll be very small. Like what? If you have a half and you square it, now you have a quarter. So if you have a small oscillation and you square it, it just gets smaller and smaller. So you could ignore the higher terms, and thus we have an equation that works. So next we'll go ahead and get you see how the book goes into the potential energy and kinetic energy. So actually we can skip the kinetic energy and potential energy. We shall figure out the position. Let's go straight to adding damping. One, two, damping. This is simple harmonic motion. H2, we will add damping. So basically, in this example, friction is 0. Like there's no friction going on. But what if we were to recreate this diagram here? And let's say that friction equals not 0. Let's say that friction is the damper. I don't know if friction inherently is related to um, speed. So let's say friction remains 0. So let's say we have a damping force that is proportional to velocity. So whatever this damping force is, it's proportional to how fast the object is moving. Let's see if friction is proportional to velocity. I don't even know. Do a search, is friction proportional to velocity? We do have to have another damping. Let's see what it says about damping. Let's scroll a bit. Yeah, that, damping. Okay, well, damped oscillations. The motion represented by the simple harmonic oscillator is termed a free oscillation. 1/7 oscillation, the motion will never cease. This opus simplifies the actual physical case in which dissipative or frictional forces would occur. Eventually damp the motion to the point that the oscillations will no longer occur. We can analyze the motion in such a case by incorporating into the differential equation a term representing a damping force. It does not seem reasonable that the damping force should, in general, depend on displacement, but it could be a function of velocity or perhaps some higher derivative of the displacement. It is frequently assumed that the damping force is a linear function of velocity. Right, cool. Online search didn't help with that one. Oh, where does it go with that? So force is proportional to velocity. So we can say that uh, uh, P equals some scalar V. Uh, and the convention is to call this scalar B, and then we end up with x dot, because V is x dot. Um, and we know that the damping will oppose the motion of the object, so it'll also be negative. So to add damping, I want to make sure I'm not adding too many details. All right. So in this case, going back to our original equation, we're now adding damping. We could say F equals, you know, say minus B dot, and it's equals that double dot. So now we have this. So this is our equation with damping, including a damping term that slows down the object. So I'll just go ahead and say friction equals not zero when F dampening is proportional to velocity, and that's sufficient for now. So solving this is a little more complicated. So it allows us to take just this part here. We can say that x double dot is m x double dot plus b x dot plus kx equals zero. And if I was to divide everything by m, we would have x double dot plus b over m x dot plus k over m x equals 0. Because again, we want to do like we did here and solve for x. But I can't just, in that case, there will be two things on the other side. As we see here, there's two things on the other side instead of just one. So it's not as easy to just for solve for it by itself. I want to be able to help to make that more clear if I add another step here. So I'll recreate what we have here to show what I mean. So we have x double dot equals negative b over m x dot minus k over m x. So this is, so we'll call this to theta, call this the same thing that we had before, omega naught squared. So here we have b over m equals 2 beta, and we have omega naught squared equals k over m. And these are using conventions that make future parts of the problem easier to solve. So as we can see, this was a second order differential equation. And this is what do we call this? We have d squared x over d t squared equals negative 2b dx over dt minus omega naught squared x. So this is a second order. I guess technically this would be a second order dE. This would be homogeneous. So I could bring everything to one side and have 0. Well, I mean, what I have here is homogeneous as well, because I could bring everything to the same side. Forget one of my favorite books is this differential equation book. These are just so well written, but I don't want to bring it up right now. Just to figure out what the wording of this thing should be. So what we need to do here, we could bring everything to one side. We can say, and I'll try to keep the same iteration I had here. We have d squared x over d t squared plus 2 beta dx over dt plus omega naught squared x equals 0. So we're going to solve this second order differentiation to get the position. And the way we normally do this is, and if I was to point out this is called the damping parameter. And this is the frequency for English frequency. All the way back. And so we have that. And if you notice, this equation that I have here is equation 3.34 in the book. And just they wrote, did I leave off an M? Okay, I'm looking at 3.35 in the book. So this is equation 3.35 in the book. We just see left the x double dot x dot and x notation. and welcome who joined. Be sure to drop a line. Let me know if you have any questions, comments. All right, so we'll go ahead and solve this. So the way that we solve this is we do what's called a auxiliary equation, where we take the second order term and just call it R. If it's second order, the second means of the second order term. We have the first order term. So the first order term just is no squared. And the zeroth order term doesn't get an R, so that just becomes omega naught squared equals 0. Now what we want to do is go ahead and solve for the quadratic equation of this form. There might be a way to just factor it. Might be a good time to practice my, what do you call it, completing the square. But that'll make things more complicated. So I would just do it the normal way. So we use the quadratic equation, r equals negative b plus minus square root of b squared minus 4ac, and everything divided by 2a. So r1 equals, oh, and maybe I should note that uh, a equals 1, which is the coefficient of r squared. B equals 2 beta, which is the coefficient of R, and C equals omega naught squared. So we'll solve this second order differential equation. It's homogeneous because I can bring all my x terms on the left side and have 0 on the other side, if it makes it homogeneous. And there might be another word for the fact that there's multiple things there, but it's not such a big deal. But the second order is homogeneous. And for the completing the square, we'll go ahead and do the quadratic equation. So R1 is going to equal negative 2 beta. I'll call this plus. We'll call the number 1 plus. That's going to be square root of 4 beta squared minus 4 times 1 times c omega naught squared. And this is all over 2 times a, which is 2. So what we can do is we can divide the 2 into everything. So this will be negative beta plus or minus. So now when I divide this 2 into the square, it becomes 2 squared. So that becomes the square root of 4 divided by 4. So that's just b squared. And then it still becomes another 4. So that's omega naught squared. And this becomes our first r. Our second r is the same thing with a minus. Oh, so this is r1. So r2 will simply be negative b minus square root of beta squared minus omega naught squared. And beta is the leftover from the damping term. Omega naught squared is the natural frequency. And so we can go ahead and plug this in. And the way it works is utilizing this method. The R becomes, if I also write this sort of the general form, we plug this in by saying the solution. So again, earlier we solved for x, we were able to solve pretty directly because of the nature of the simplicity of that differential equation. For this equation, when we solve with the auxiliary equation, we use the exponential. Like I said before, you could either use the exponential form or the trigonometry form. So the form of this becomes x equals a1e r1 plus 2 to R2. Simple enough. So that means that my solution becomes x of t. And remember, by the way, that later I'll come back and maybe I should put that I'll do a relativity soon. So I think I have an extra thing for, oh, did have a rate my writing here. Maybe I'll just, you see I'm writing a whole lot better in text. So I'll call this rename, I mean, repurpose relativity next. So I want to remind y'all that I'll be doing special relativity next, so you don't want to miss that. And I'll put this where people can see it. Hard to see right there, isn't it? Let me change the color of this text here. Y'all let me know if that's good enough to see. Special relativity next. I think it is. Let me know if I should change the color on that. The special relativity is next. Keep that in mind. So x of t then becomes a1e. And in the numerator, we'll have negative beta plus square root of beta squared minus omega naught squared plus a2e negative beta minus square root of beta squared minus omega naught squared. And we can simplify this a little bit. I think I shall leave it in that form for now. Oh, when I do that, I'll bring it right back. Oh, all right, there we go. So you see the textbook sort of simplifies it a bit more and track some stuff up, but I think I'll just leave it like this for now. Right, so that's the thing for position. And you can see how it gives us different criteria here. Now, the way that this impacts us in various ways because different types of damping, different amounts of damping will have different effects. And there's a chart in here that shows the effects of it. So under damping, you can see that it has a lot more oscillation, a lot of back and forth. Critical damping, it slows down very gradually, very smoothly. Over damping is more gradual. So that means that like the brakes on our cars, the damping force that it puts on our drive would be more critical damping or over damping because under damping it have us, rocking a lot. Or if you think about those doors that have the little pistons on them, so when you let them go after you open them, they don't close very quickly. They don't slam close. They might start fast, but then the damping slows it down. So that would be either critical damping or over damping because otherwise it would just be banging against the wall a few times. And you've probably seen doors where the piston was broken and it did that. It banged against the wall a bit. And I might take instead of removing my layers as I warm up through my teaching. I got my longhorns on my outer layer and my SMU on my under layer. So I'm representing both of my universities today. Most of my winter gear is still from UT, so I might eventually buy some SMU gear for winter. I have like a lot of t-shirts and stuff. Right. So looking at this, we'll pass it. I was showing you these screens. So under damp, means that omega naught squared is greater than b squared. So going back to the illustration that we looked at earlier, the if the angular frequency is greater than the damping function, then it's underdamped, which makes sense. The frequency that's pushing it is bigger than what's slowing it down, so it's underdamped. The damping is not as strong. Critical damp, omega naught squared equals b squared, and overdamp, omega naught squared is less than b squared, which makes sense. It's overdamped if the damping is bigger than the frequency. And let's see if that should do anything else on this one. Well, I'll go ahead and move on. And I'll do one more step to this and add a driver. And then I'll take a break and move to special relativity. So let me make sure I don't miss anything that I want to cover. Position, I think we're good. I think we're good here. All right, so the last thing we're going to do is we're going to add a damping function. So I'll say A, what was I calling it? The numbers, A3. So now we have driven damp. So if I were to copy this illustration down one last time, we can say is not only do we have the friction equals not zero, not only do we have our K, our spring constant of giving us a restoring force, let's say that we also have a machine connected to the mass, and we'll say that this machine is adding a force drop my head speed. I need to make my box a bit bigger. We have a box with a visual force. If you start the mass moving, this piston can move back and forth. Wish I could draw it better, but is an engine that can adjust the thing and move it back and forth, right? So even if you set it going, that driver is going to eventually take over and just be moving the mass back and forth, and we're going to get the equation of motion for that. So it's very similar to what we did before. So I may be able to save a little bit and do this. I'll copy all of this. This is written so very nicely. And the only addition we have to make to have it driven is going to be that on this term, the terms on the left, I'm going to add my f of t. Right. So you notice that the normal uh, configuration for classical mechanics still holds, in that this is ma, mass times acceleration, and mass times acceleration, F equals ma is F net. So every single force acting upon the system has to be on the other side of the equation from ma. So this is F equals ma, Newton's second law, if I remember right, the numbering. Um, and every force equals a mass times the acceleration. And then the left side is the particular forces all added up. That sums up to give us the net force that's going to equate or result in the acceleration that we see. Right. So all the different forces that are acting on the body ends up being the acceleration that that mass experiences. So here I can also put plus ft over m, right? Because the ft was on the side by itself. And I can move this over a little bit. And we'll call this plus a. Let me do this. Let me add another line. We'll say here that ft equals a sine of omega t. Right? So the omega here, you notice there's no subcircle, it's the driving frequency. And then we can say that actually, I'm going to mess up my notation. So it's not A, we'll call it F naught. F naught sine omega t. So then we can say that A equals F naught over M. So then I'm going to move this entire thing there. We're going to have this Ft divided by M is actually F naught sine omega t divided by M. So now we have A sine omega t right there. And going to be incorrect now. Going to have to call it something different. This is plus A sine omega t. And now it is non-harmonic because when I bring it to the other side there, I still have A sine omega t. Sometimes I'll do a shortcut that I learned from my uh, professor in my mechanics lab. He has a shorthand where he sometimes does sine of theta. He just calls it S theta when the equations get really long. I notice I fell into doing that right there because we do get into some long equations in graduate school. And I find that the only way I can fit the equation on a line is to do that if I want to get it fit all on one line. But we don't need that convention right now. All right, so we have this. So that's a damping parameter. This is still the natural frequency. And this is the uh, driving force. Now we have a simple harmonic oscillator. As long as the oscillations are small, it's a simple harmonic oscillator. We have a damping parameter, F equals not zero. We have the natural frequency, which means you can see the spring. It's going to be a natural frequency given the spring and the mass. But we also have a driving force that will eventually overtake the entire system. And now we have a more complicated equation to solve, because we still have to solve this equation to find out what x is to discuss the position. All right, so the way that we solve this differential equation, and by the way, this is a second order non-homogeneous uh, the second order, because the highest term has a second derivative, is non-homogeneous because we can see that there's something on the end over here. It doesn't equal zero, and it's a differential equation. All right, so the way that we solve these types of equations is we break them into two parts. So we have one half where we have and make sure I use the proper word, the complementary solution. That word, complementary solution. Yeah, complementary solution. So complementary solution where a equals zero. So if a equals zero, what we end up with is this. We already solved that. We solved that earlier where a equals zero. We just get that. So we're writing another solution to that. Right? We solved this. That's just the damped system. So the solution for that is called the uh, complementary solution. So the complementary solution, I'll just copy that down. I didn't simplify it, but I may end up simplifying it in a moment. I have to remind myself what comes up later in the notes. But we have this. I'll call this the XT complementary. So that basically the solution has two different parts to it. And then we have the particular solution. Right? So the particular solution is the solution given that we have our force to the other side. So let me do particular solution. A equals not zero. And the general solution will be the sum of both of these. So we'll get to that point. So we're going to guess particular solution. And this is going to work quite interestingly. So check this out. We're going to guess that P particular equals D sine omega t minus delta. So we'll guess that as our particular solution. So we guess that we have to actually plug it in to see what we get. And in order to plug it in, we see we have to get a second order derivative of that equation. So x dot t equals, so now we have d cosine omega t minus delta. So we have to take the derivative of, and one thing I'll point out as well, by the way, this does not have a sub-zero on it because it's a driven frequency. It's not uh, a frequency that's normal to the spring. It's a imagine there's a gear on this thing, We can go ahead and change this thing, uh, to whatever frequency we want. So, and manually set omega. Right? So the omega naught frequency will be based upon the mass, based upon uh, uh, the K value of the spring. We get that mass, that spring, it'll always operate the same. But this one we can change it however we want. There's no omega naught. And we have the second derivative. Oh, and I forgot one term. Left a space for that. The second derivative is going to be negative d. And you can see where this is going. Sine omega t minus delta. Just like we did before. Take the second derivative as a cosine, so a negative comes out. We have to do the chain rule, take the derivative on the inside again, and thus we have that. So what we do here is, to solve for this, we're going to actually plug our guess of a solution into the full thing that we had there. So if you recall, this is our full setup. Now we're solving for the particular solution. So I'm going to literally plug what I have into this. So I have first the second derivative of the particular solution. That's literally this. Let's copy it down. Then we have plus 2 beta times the first derivative of the particular solution. So I'll copy that down and put that there. And then we have plus omega naught squared, the particular solution that we get, which is this original one here. And that's going to equal a sine omega t. And I'm almost do a little shortcut where I did s before. Now what we need to do here to simplify this thing is use a trig identity, a trigonometric identity, even though the yeah, easy enough. And which one are we going to use? Guess we're going to use, negative one. The negatives and positives here. I only have negatives. I believe. Do I have a plus on one of them? Let's see. Let's write it out. So one identity is if you have, well, that's why, because one of them is sine and one of them is cosine. I forgot about that. So if you have, I'll write this also in blue. If you have sine a minus b, that's going to equal sine a cosine b minus cosine a sine b. And if you have cosine of a minus b, you're going to have cosine a cosine b plus sine a sine b. So the sine one, we alternate the sine and cosine. The sine of the first term is first, and then you subtract the opposite with cosine of a. And the cosine one with the minus doesn't matter because they're going to be summed with each other. But just note that the cosine is times the cosine of, either term plus the sine of either term. What we're going to do now is plug this in. So I'm going to have negative b omega squared. And maybe now I'll do the shortcut I was telling you about. So we're going to say that this is s omega t. Now look to where. Let me go ahead and just write it out. We're going to have sine omega t cosine delta minus cosine omega t sine delta. The first term, and then we're going to have plus 2 beta b. Now we have the cosine one. There's cosine omega t cosine delta plus sine omega t sine delta. And then for the last term, we have plus omega naught squared b. It's important to keep up with the knots so we know which one is the normal frequency for the spring of mass and the other is the frequency for the actual oscillator. So here we have the sine one again. So I'll just copy that one down, assuming I wrote it correctly the first time. And this is going to all equal the a sine omega t. And looking at my notes, look pretty right. I think we're in business. All right. So now it looks pretty complicated. The idea that we're doing here is to extract out, basically we're solving for D, basically. We're doing all of this to solve for D because we have the complementary solution already. We know what that is. And all we have to do is solve for D to get what we need for the particular solution. And everything works out. So we find out what D is. We can find out what to replace D with and have our particular solution. That's basically the idea that we're doing. Let me make sure I didn't miss anything. Yeah, looks like we're good. All right, so now we're going to do this. There's a little bit of algebra here that's going on. So first thing I'll do is distribute this. So I'm going to have negative d omega squared sine omega t cosine delta. That's distributing this here plus d omega squared cosine omega t sine delta. And that's distributing this here. The two negatives make a plus 2 beta b cosine omega t cosine delta. That's distributing this here. So we have plus 2 beta b sine omega t sine delta. That's distributing this here. And then we have plus omega naught squared b sine omega t cosine delta. That's distributing this one here. And then we have minus omega naught squared b cosine omega t sine delta, distributing also equals a sine omega t. And actually, I'll bring this to the other side. We'll say this is minus a sine omega t equals 0. So now what I can do is, since I've brought this to the other side and I have everything equal to 0, we know that whatever this is, whatever this left side is, and it looks all ugly and crazy, but whatever is on the left side, it must all together equal zero. So that's the benefit of, that's why this homogeneous one was so easy to solve, because we know everything on the left side equals zero. It's just a lot easier to solve. We could just use the quadratic equation. But here, we had to basically force it to be zero. I guessed the solution and plugged it in and made it zero on that side. So now all I have to do is just strategically select like terms, and I can solve for what I want. And one of the things I notice is I have a sine omega t here. I have a sine omega t there, a sine omega t there, and I have a cosine omega t here, cosine omega t here, and a cosine omega t there. Now and I left out one sine omega t. Now the benefit of identifying this is, remember that we're solving for the driven form of the oscillator, in which we have a omega, a driven frequency. So I'm going to go ahead and get all those driven frequencies by themselves, and that'll help make things easier for me. So I'm going to go ahead and start with sine omega t. And if I look at the first one, I'm going to have negative d omega squared cosine delta. That's this first one here. Then I'm going to have plus 2 beta d sine delta. That's subtracting that one there. Then I'll do this one here, which is plus omega naught squared d cosine delta. And then we just have a minus a. And we can see how that works out nicely. Then I have plus cosine omega t, getting the other cosine omega t out since we're looking at the particular solution. So I have this one here. So that's d omega squared sine delta. I have this one here, plus 2 beta d cosine delta. And I just have one more for that. So I have minus omega naught squared d sine delta. Right. And this all still equals zero. Right. So now I'm getting closer to solving this thing. So what I'll do now, I can actually pretty easily get this worked out by working with the sine coefficient and the cosine coefficient separately. So we'll do that. So we'll start with the sine coefficient. So this is our sine term right there. So I'll take the sine coefficient. In other words, what I'm saying is this sine is never going to equal zero, because this sine is being driven by a mechanical driving force. So as long as this machine is there and we have it turned on, it's never going to run out. Right? So you can imagine this, there's a solar panel there. It's getting its heat from the sun. There's energy from the sun, and it has a battery on the inside so it can stay charged. So it's never going to run out. It's going to keep going forever. So sine omega t is never going to equal zero. So what I'm going to do is I'm going to say, since sine omega t can't equal zero, that means that this entire thing has to equal zero. It has to, because sine will never equal zero. So I can just solve this for zero and make my trouble solving this a whole lot easier. Right? So some more algebra. We have C of a cosine delta on both of these right here. So this can be omega naught squared d minus d omega squared cosine delta. That's these two. And then we can say plus 2b. Did I leave off a term? I think I might have left off a term. Uh, um, a coefficient. Hold up. Looking at my notes, looks like I'm missing a term that I didn't write. Hold up. Let's see here. I think when I was distributing, I dropped a term. Yeah, I did right here. And, right here is a 2 beta d omega. I dropped an omega there. But that means that the second line here, I mentioned omegas. And here, and to the cosine is mentioned in omega. There we go. So now we have all of that worked out. So going back to our sine coefficients where we're extracting everything out, we have actually 2b omega b. Oh, I forgot one more place to write it. To be omega d sine that. And then we have minus a because the cosines have been consolidated equals 0. Next, we can extract d out of each of these, right? So we have d omega naught squared minus omega squared cosine delta plus 2b omega sine delta. And that gets the d's out of that. And I'll go ahead and move the h to the other side. So in one move right there, I factored out the capital D, capital D, capital D, and we have that. So now I can put A divided by D equals all of this. So now we're getting closer to solving for what we need. A divided by D equals all of that, right? So we can say I could invert this whole thing. And we can say that D equals, so if I invert that, A is in the denominator now, and I can multiply to the other side. And if I invert that, all of that is in the denominator. So I'll just copy it and put it in the denominator. And now we have this. So say we were trying to solve for D. because that's the coefficient of the solution that we guessed for the particular solution. And now we have what D is in terms of from the sine. We could do a little bit more with this. Which say D equals A over square root of all of this squared. Square something and square root it, it brings you back. And I can let you know that I didn't do all the algebra for this myself, but with a whole lot of algebra and stuff that goes on, you end up with this. So I'll just go ahead and put the final form. But this form is in the book. They probably did some all kind of identities and all kind of stuff. So I'll just go ahead and plug it in. All right. Square B squared. We do know that sine squared plus cosine squared is 1. I'm pretty sure they used something to do with that. I'm not sure what they did with the coefficient, but suffice it to say, it comes up to that after you do some magic and stuff. All right. Now we'll do the cosine coefficient, and then we'll go ahead and I'll wrap up and take a break, and we'll come back and do some relativity. So again, all of this equals 0. The cosine omega t is not going to equal 0 because it's being driven by the engine. So you see that that's an omega with no omega naught on it. So that means we need to go ahead and solve and find out what we're working with there. Right? So the first thing I could do is I can extract capital D. So I'm going to do that first. With this. Like so. And we already know what D is. We don't have to really focus on it anymore. So if I divide both sides by D, I end up with this equals 0. And what we can do here is some Machiavellian uh, uh, trig type stuff. Everything here we technically know except B. And let me check one thing. So really we need delta. Figure out what delta is by a long process. All right, let's do that. So the idea is to find out what delta is. I have a lot of trig stuff here, so I can do that. I have to manipulate some things around. The first thing I'll do is solve for B. So we will have 2 beta omega cosine delta equals omega naught squared sine delta minus omega squared sine delta. So I can go ahead and divide by 2 beta. So that gives me, well, 2 beta, but 2 everything else. 2, I want to get beta by itself. 2 omega cosine delta. 2 omega cosine delta. What I have here is b or beta equals uh, omega naught squared sine delta over 2 omega cosine delta minus omega squared sine delta over 2 omega cosine delta. So that's going to equal omega naught squared over 2 omega tan delta minus omega squared over, oh, well, omega squared over 2 omega. So, yeah, keep it together. So I was about to cancel one of them, but it'll work out better when I consolidate tan delta. So I can factor that. So this will be omega naught squared minus omega squared over 2 omega tan delta, right? Beta is the damping frequency. So that's not B, that's beta. That's the beta from way back when we did the damping one. So we can say that tan of delta of our driving component. So again, we have, I'm not sure I named it something different. I have a delta there and I call it, maybe I should call it delta prime or something. Right here. Prime on all of these. Differentiate it from the one that's in the original offset. So you can start your driving engine. You can start that whenever you want. So the phase will be different from, at least it can be different from the default one. And let me know if that's not clear. But it could be the same as well. But I would put a prime on it to identify that it could be different. Get to the final solution, less confusing, or more confusing, depending on how you look at it. All right. We have tan prime equals 2 beta omega over omega naught squared minus omega squared. That means that delta prime, the phase of the driving component, is inverse tan of 2 beta omega over omega naught squared minus omega squared. So now we can put together our final solution. So as I said, the general solution. So I'll finish this final solution and I'll take a break and then we'll come back and do some special relativity with the muon experiment of how muons survive all the way into the atmosphere. Only that's a proof for general for special relativity. So the general solution is going to be x particular plus x complementary. So it's going to be x g t. Right. So this equals the general solution with the complementary solution. What was it? Is this I still never simplified it, but it's all right. You just multiply some stuff and factor out some stuff and um, look a bit snazzier, but it's not really necessary. Have this. And I will simplify it so I could demonstrate something. But then we're going to have plus. All right, so remember our guess particular C was D sine of omega t. Right? Going back to our guess here, minus 5 prime. How can I forget that minus 5 prime? All of those, um, anything else here. I think I got all my typos. That's important so that we don't see all that word for delta, drop it. All right. Uh, so our A is going to be, what was it? D. Another typo. Hopefully I didn't. Oh, all right. I didn't change it too much. That was from the original equation, not the solution. Okay, hold on. Even though I do need my parentheses there. Okay. All right, there we go. I think we're good. So that's going to be A sine omega t minus delta prime over. This is basically just plugging this in here, right? Square root of omega naught squared minus omega squared squared 4, I'll say plus 2 omega beta squared. And I need to write this a bit neater. Squared. Right. That's our solution. And we have that the delta prime in our final solution is tan inverse of 2 beta omega over omega naught squared minus omega squared. All right. So now we have this worked out. We've solved this entire thing. I think I caught all my typos. Hopefully I did. I'll scroll through one more time briefly. Yeah, I think I got everything. This is our guess. And we plugged in the A for that. This was our original equation. And we need to make more different letters. So the A was the one, the driving force from the driving machine. Boom, boom, boom. So A is still on the driving machine. A is on the driving machine. And uh, plugged in the one with D from the guest. So the guest had a D in the solution. Boom, A from the driver. Yeah, I think that's all. I think I almost changed that A into a D that would have thrown everything off. Let's do the guess for the solution for the particular. Boom, boom, boom. And okay, so there we go. I think we're good. And this A should be, if you go back up here, ironically, the A should actually be the F naught over M right here. So that should actually be the same thing, right? Because that A is the one that was in the equation that we substituted for the original amplitude of the driving force divided by mass. So we know that the particular solution, which makes sense, the particular part of the solution is going to have an amplitude based upon the driving frequency, right? So the motor is going to go at a certain distance, and that's just the distance it's going to have. So it makes sense that the particular solution will have that. But notice that the amplitude of the general solution is back here, which means that when you first start let's talk about what that means. Well, so in order to do that, I'm going to have to simplify this a little bit. This is what I was avoiding doing earlier, but I'll go ahead and do it now so we can see what actually happens with this. So, and I'll try to write this pretty small. So we'll say B X G T equals A1 E negative beta E square root uh, B squared minus dot squared plus H2 E negative beta E negative square root B squared minus omega naught squared plus everything else remains the same. And I'll go ahead and copy everything down initially. So what I'll do is extract out the E to the negative B power. So I'll just put this one in the front right here. It means this one is going to be factored out. Let's delete it. And now I have this. I'm going to factor one of these out. Right. So one thing we can notice is since this is a damp driven oscillator, the E to the negative B relates to the damping. And oh, I left off a T somewhere. Crap, I'm going to leave off a T. I left off a T on everything. So let's go back. It's going to change over time. So there's a T here. Everything is changing over time with X of T. That's the general solution. But that means I must have forgot it on my first solution as well. So there's a T multiplied by everything. Doesn't really matter where you put it in the front or behind. So maybe another video we can talk about converting between exponentials and trigonometric functions, how that looks. Sure, I have all my keys. I'm glad I'm showing you the details so I would have probably missed that variable there. And we do have a T in the front on these. All right, there we go. So what we have here is as that relates to damping. So as we can see, as T gets bigger, the negative exponent means that this is actually 1 over e to the beta t. So that means that as time increases, as it progresses to infinity, this term gets closer and closer to 0, which means that after a long amount of time, so as t approaches infinity, e negative beta t approaches 0, which means that over a long time, only the driving frequency is seen. So basically, if you have this oscillator, let's say that um, we do this. Let's say that no, I'm not gonna say that. It's not gonna hurt having more than one. Now let's say that um, when off, well, let me write it rather, but let's say when this is off, the device is off, it causes some resistance on uh, the mechanism advancing. But when you turn it on, it's also caused a lot of resistance because it's driving. But what happens is the oscillation of the mass blends with the oscillation of the driver, and you have a sort of blended frequency. You know, maybe the normal frequency goes like this, maybe the driver goes like this. But when you start the thing oscillating, then you turn the driver on, maybe you have something like this. You know, it'll look like it's, mixing between the two. But the driving frequency is going to be constant, while the natural frequency of the spring is going to be damped, so it's going to constantly go down. And eventually, the mass won't have any oscillation from the spring at all. It'll be only the driver that's pushing it because it's oscillated down to 0. And you basically, what you just have is just the driver moving the mass. That's why I say it's over a long time, only the driving frequency is seen. Because as t goes to infinity, e b to the t goes to 0. So that's all going to 0 out. All right. And let me see if there's anything left I need to do before I close up. Like I said, I'll close up and come back and do some relativity. You definitely want to come and see some of that. Do one more thing. And let's say, go ahead and simplify this equation. Uh, so underdamp with the underdamp. Omega is greater than. So let omega 1 squared equal omega naught squared minus beta squared. Because I have that in mind. That means that uh, omega 1 squared equals beta squared minus omega squared. That's what I have to reverse in my numerator. So what I can do to simplify this is, so we have x t equals uh, a1 t. I wish I would have simplified this part earlier. I can do after I simplified it. So you just hate this button being right there. I'll put this here. Leave it now. Hold on. Right. Okay. All right. We have xgt equals. And after, let me just copy this down, and we'll do one more simplification before I go. To take into account the fact that it's underdamped and what that looks like. I'll call this a what? A4, A3, A4. So that's A3 right there with the damp driven. A2 was the damping. So A4 under damp. So B minus that. This means we're going to have negative omega 1 squared under here. Negative omega 1 squared there. Looks right enough. So now one thing to keep in mind is that I equals negative the square root of negative 1. That's an imaginary number. Let me know if you're interested. We could do a video about that. Imaginary numbers don't mean that it's literally imaginary. It just means that the axes that it relates to is in a frame that's not easily represented uh, in three-dimensional or four-dimensional space. Like when you get into quantum mechanics, I is there a lot because there's quantum mechanical things that can tunnel and things like that. So my understanding is that it sort of like refers to a avenue of space that's not necessarily familiar to us, but mathematically it makes this, you know, phase of space, this angle of space conceivable. So if I was to rewrite this one more time with that taken into account, and we see we have a few negative ones in bracket. So this means that this becomes this negative square root of 1 here becomes I, and the negative square root of 1 here becomes, we have that. And what else can we do here? Oh, now we have just that squared. That simplifies things. All right, maybe I have to do that in one. I have to make another line. So now I have this omega 1 squared square root, omega 1 squared square root. I'm going to make both of those go away. Now I have this. I mentioned I might do a separate video to show this, but I can go ahead and show it now. So now we have the numerator, the exponent, I mean to say, in a form where there's a imaginary number in it. There's an exponential. So we can go ahead and utilize the fact that you can convert between trigonometric functions and exponentials when you have an imaginary number in the exponent. And what we have is this um, A cosine omega 1t equals A E I omega 1t plus E minus I omega 1t. Right? So what we can do is go ahead and substitute that in. And now to go ahead and call uh, the uh, coefficient between them A. So I will go ahead and call this, and yeah, let me add another step. That's sufficient. We have A cosine omega 1 t minus that. Right. And, remember that omega 1 equals the angular frequency of that. Right. So that's that. So thanks all who watched. Hopefully you like and subscribe if you haven't already. And what I'll do is take a break. When I come back, I'll do some special relativity, and we'll look at the paradox of the fact that there's uh, particles, subatomic particles that are reaching the surface of the Earth that we can measure, but the half-life of these particles should cause them to decay before they reach the surface. And we'll see how it's a proof or a demonstration of relativity that those things reach. So give me about 10, 15 minutes, head back, and we'll get started. And I'll set that for the top of the hour. So 10 more minutes, I'll be back. I'll see y'all then.